I'm Alex. I'm a dev. Nothing more to that. I'm going to have a talk called The Path Down Covenant Road, which is going to talk about the Toccata upgrade, the ZK upgrade, and how to build on Kaspa now that we have all these crazy new opcodes that allow us to do a lot of different things. So first off, I just want to thank all of the participants that were involved in the Toccata upgrade. I don't know the names of all, but thank you everyone for helping us make it a reality. It was a great effort by a lot of people. We encountered a lot of difficult problems, and together we solved them in order to make Kaspa a better chain. So we're continuing as in the theme that we have, the line of music. As Ashton mentioned, the crescendo upgrade gave us the foundation that we needed, the 10 blocks per second, some already introspection opcodes in KIP 10. Now Toccata gives us pretty much full expressiveness. We're able to control in any way how money moves on Kaspa, and that's the core principle. It's basically a UTXO script, but now it can see itself and decide whether it should be unlocked or spent. So the Toccata scripting comes in 3 different pillars. We have enabled some more compute opcodes, which allows you to perform more complex computation, such as division and multiplication. Although it sounds very primitive, it's very important when it comes to advanced scripts. The second pillar is the introspection. In order to force a UTXO to continue the lineage and basically prevent its behavior from changing after being spent, you need to enforce some rules, and that's why the UTXO needs to be able to see itself and introspect on itself. We're going to go in a bit more detail on that later. Secondly, we have the proving pillar, which is, you probably know, I am the author of KIP 16, that introduced the ZK opcode to Kaspa, which allows you to verify a Stark or a Snark via Groth 16 proof on L1 right inside the UTXO script. We're going to go over what that means as well. So before that, I'm just going to introduce new developers who might be familiar with the EVM ecosystem or other languages into how to script in Kaspa. So basically how it works on a high level is that you have, you usually when you do scripting, you use a pattern called P2SH. The P2SH pattern works in the way that you first create your smart contract, which derives the rules of how it should behave. So let's say that you only want for it to unlock after a specific time or by a specific person, and this is called the locking script. With the locking script, you basically hash your smart contract here, and then you compute the hash, and then you ensure that it's equal afterwards. Now, the node doesn't store your script. It only stores the hash of your script. So there are some implications with that, and that means that you need to store your script somewhere. There are various design alternatives for that. Now, when you actually want to interact with a smart contract, you provide the signature script. The signature script is different for all kinds of scripts. For a regular transaction, it can just be a signature from your private key. For a ZK interaction, it will be a proof. And the signature script is basically this data that you put in, followed by the redeem script, which is the script of your smart contract. I'm mentioning script a lot of times. It'll be clear as we go on. We have a lot of examples. So, just to show a bit about the opcodes that we have introduced. So at the top one, we have the opcat, which basically allows you to concatenate 2 strings together. This might sound very primitive, but it's extremely important for advanced computations such as ZK, when we need to reconstruct hashes or break them down and so forth. We also have opcodes that introspect on the input of the script public key or the payload. We have an op substring which takes a substring of whatever is in the input and allows you to basically compare and see if the input is what you expect it to be. I'm going to talk a bit more about the opcodes. As you can see, we have different kinds of opcodes, and I have organized them into different categories. First, we have the shape, which is basically allowing you to constrain your script to, for example, the number of inputs, or the outputs, or the version of the transaction, or the lock time, which is basically a way to have a notion of time inside the script. This is how you, for example, can do atomic swaps. And also I want to just briefly mention that some of these opcodes have already been existing in the Crescendo upgrade. So this is the full list of the Toccata opcodes can be seen in the repository. But the reason why I'm mentioning them is because they're still valuable and we need to see the whole picture. Because if I only were to describe the Toccata opcodes, it might have been, you might have missed the picture. Yeah. So one interesting thing that was introduced in the Toccata upgrade is called the covenant ID. And so the issue with the P2SH pattern is that, let's say I make a NFT transfer. The owner of the NFT, or let's take another example. Let's take like ERC20 tokens. So the ERC20 token might have a value inside, inscribed into the contract itself. Now let's say the value changes. This will mean that the script, your smart contract script, will change, and therefore the state will change as well, which means that your P2SH hash will not be different. So how can you now tell apart from what was before and after? You might have some state before, and then you change it a little bit, but because we all know all hashes are unique, when you change the input, the hash changes. So how can you connect them? We need a unique identifier. This is the covenant ID. The covenant ID is basically here. It's identity. It guarantees that the lineage is real and unbroken. You introduce a covenant ID by calling a specific function inside of the transaction struct in the Kaspa repo. So with the covenant ID, we basically get the equivalent of a contract address in the EVM ecosystem. This is the contract address for which indexers can build an index of contracts similar to Etherscan. Then we also have the behavior, which is what I mentioned before, that you cannot just have a contract ID and then expect it to behave in some way. You must enforce the behavior by using the opcodes that I mentioned in the previous slides. So this is going to be a bit small, so we're probably not going to be able to see everything. But basically, this is how a UTXO script could look like in its internals. This is an example I wrote, which is basically an NFT-like coin, where on every transfer we enforce a royalty payout to the creator. I'm not going to go through this entire example since it's quite small, but I'm just going to point at some interesting parts. For example, over here, we enforce that we pay the royalty to the creator. Just to see here, for example, the OPTX output SPK is basically retrieving the output of the script public key, the script public key of the output. The output that we have selected as the argument is output 0. In this script, we've basically enforced that the output at index 0 always goes to the creator of the NFT, so basically the royalty. And then we have a hard-coded address here, which is updata 36, the creator of the NFT. Now, we validate that the output of the index at 0 is equal to this hard-coded address. So basically we're enforcing that the output at index 0 goes to the creator of the NFT. Now, so we've verified that. Now we do that with op equal verify. Similarly, we again pass in op0 to we want to access index 0 again. We want to access another introspective opcode, the optx output amount. We want to know, okay, how much is going to the output 0. And then we validate, we put in the minimum amount of royalty that has to go, which is in this case a hard-coded floor of 1 Kaspa. And then we validate that it's greater to or equal to the output of 0. So essentially, you cannot give less than 1 Kas to the creator. Otherwise, this opcode would reject, and it will fail. So this looks a bit complex, but if you just stop viewing it in the whole as a whole picture, and just after this presentation or at some other time, look at this example and step by step, I think it's quite logical, because you always have a stack which contains the data, and then you have opcodes that do some specific task only. And then you just go step by step, blah, 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 blah. It will verify all these things, and then everything's great. You can transfer your NFT, and the job is done. So, what do covenants unlock? I wouldn't say that these things are only possible on Toccata. If you're creative enough, you will probably be able to do them on Crescendo as well. But Toccata makes it certainly much easier. We can, especially with the ZK opcode, with introspection, you don't no longer need to rely as much as on external infrastructure as before. Now you can do it straight on L1, which is good, because L1, that's where we have the proof of work. That's where we can enforce logic. So, as you saw before, we went through an example with raw opcodes. And that might have looked quite complicated. And so there's obviously a big learning gap, or it's a very big learning curve to get started writing smart contracts with raw opcodes. So therefore, the core team has been working very hard and to simplify this and to create a scripting language that is similar to, I would say it's quite similar to Solidity, but it's inspired by Cache Script. And it looks something like this. It looks similar to Solidity and has similar behavior like Solidity, which allows us to, with more ease, integrate ecosystem developers from Ethereum to Kaspa. This is still an early stage. But if you're interested, I recommend you to start and visit this link and check it out. So now I'm going to talk about zero knowledge. So basically, what is zero knowledge? It may sound very cool. It's quite cool. Basically, what it does, it proves that you have executed something without actually showing the entire execution trace. Usually when we run something on a computer, we run it, and we can actually trace the entire execution, because we can look inside the memory, we can see where all the addresses are and move it. But how can you prove that you ran something? I can tell you, I can run something on my computer, and there's no way for me to show you that I have actually done this. However, with math, complex math relationships that exist in our world, we are able to commit to certain things which allows us to prove that we did something. So I'm just going to leave it at this abstract thought that basically you can prove something without showing the entire execution. So this allows for two concrete things. First, it's privacy. Basically, you can prove that, let's say, a transfer occurred without showing who the recipient is, or the sender, or the amounts even. And in addition, it's also that you can compress execution output. You don't have to show the entire execution to the L1 network. Rather, you can just show it a small proof and say, okay, hey, this happened, and you can be very sure that it happened. This is not a new technology. It's been around for quite a long time, almost 10 years. About 10 years ago, Groth 16 was introduced, which is one of the most used ZK protocols. So essentially what ZK allows us is to always know that something is truthful. You cannot fake the proof, and the verifier doesn't need to learn anything. You can restrict it into any way you want. So at Kaspa, we have decided to integrate a RISC-0 ZK VM approach, which verifies succinct receipts, and also Groth 16. For RISC-0, it's a ZK VM written in Rust, and what this specific precompile does is that it allows you to prove that some program produced some output with this proof. And this program can be anything, and it has to be written in the RISC-0 IDE, or the environment basically. So on Kaspa, we have introduced opzk precompile. It verifies a ZK proof inside a script. It takes a number of arguments. There are two tags, as we call them, where you can choose which precompile you want to execute. You can execute Groth 16, or you can execute RISC-0. Both have disadvantages and advantages. RISC-0 is a Stark, it's quantum safe. Groth 16 is not quantum safe. But it's much smaller. The proof size is only 192 bytes, whereas RISC-0, as in the configuration that we have created, it's about 200 kilobytes. Now, there are specific restrictions for which kind of RISC-0 proofs you can provide. I'm going to go over them. So, just briefly, how does the opzk precompile bind the proof? There are a few arguments. There's I'm not going to go into detail on all of them, but the seal here is the actual proof. The journal is basically a document where your ZK program writes in, and that's where you put everything that you want to prove. Like, let's say a program outputted, transfer some money here. Then that's where you put it. The image ID is a unique identifier to a program. So, for example, if you write a program in RISC-0, you get a unique image ID, and that allows you to say that only your image ID outputted this thing. If you're an L2 network and you want to prove, let's say that someone has exited, you have a unique image ID for your L2 network, potentially. And with this, you can prove that, okay, your journal contained that a transfer to some address and no other L2 network. So essentially, the image ID binds to the program. So again, what can we build with ZK on Kaspa? We can build cross-chain state proofs. For example, as Pavel mentioned, although I don't know the exact details, but there's something called the signal protocol in Ethereum, which basically allows you to publish a global root on Ethereum, which allows you to then verify against. So the signal protocol is an initiative across many chains. For example, if someone was to integrate this, we could have a known root on Kaspa, which people could make ZK proofs against, and then securely, non-custodially perform actions there. Private computation, you can have private programs, you can have private protocols, privacy transfers like privacy protocols, trustless bridges. You can prove that something happened on some chain and therefore release the funds. A surprise. I have built atomic swaps on Kaspa. Atomic swaps, it sounds a bit nuclear, but there's no nuclear activity involved. It's just hashes, unfortunately. Or, yeah, maybe not. It's called Strom. Strom in Swedish is electricity. It's also flow, like the flow of water. And over the flow, there's a bridge. That's where Strom finance is. It's fully atomic with 0 trusted parties. It's basically either your swap happens or not. It's obviously relying on the security of the HTLC contract, which is public. However, there's a problem with atomic swaps, and that's that previously, because it's not a new technology, it's been around for many years, I didn't invent not much here, except I combined things in an interesting way. Basically, there's a P2P network. The P2P network allows nodes to be constantly live, waiting for someone to request a swap. This is similar to something known in the crypto industry as an RFQ model, which is a request for quote. Basically, the user comes in, asks, I want to swap 100 Igra CAS to 100 CAS. And an LP node, if it's there, it will answer. The idea is that it should be there. Obviously, this means that liquidity providers are required. But the thing that we have achieved here is that the liveness criteria kind of diminishes here. Because if we have committed LP providers that run these nodes, we essentially have very quick swaps. It's almost not distinguishable to any kind of bridge or swap. In the future, okay, first I'll talk about supported networks. So for the testnet, there are 3 supported networks at the moment. The Galleon testnet on Igra, Kaspa TN10, Ethereum Sepolia. There could be other chains in the future. But the primary focus of why was this created, it was so that you can easier exit Kaspa and easier enter Kaspa. Because, I mean, there are some ways, but I think most people use a centralized exchange to enter Kaspa. So this allows for the decentralized ecosystem on Ethereum to enter Kaspa. The thing about atomic swaps previously is that you had to go in and claim your funds, because it's like a party over there locks the funds with some secret, and then they tell me the hash of it. Then I lock the funds with the same secret. Once they reveal the secret to claim my funds, they automatically reveal the secret to me so I can claim their funds. That's why it's atomic. Now the issue with that is that I actually have to go and actively claim here. But that's a problem again with the liveness. That means that, let's say you want to do a swap, and then you want to get some coffee in the meantime. And then you come back, and your swap is not finalized because you didn't press the claim button. That's where I introduce CCR, which is Competitive Claim Rescue. And that there's a network of solvers, which are also part of the P2P network, which help fulfill your swap. They also help refund your swap. Let's say your electricity went out and you are unable to claim. There's a risk that you won't get your money, or that you have to refund your swap. So therefore, the solvers fulfill your swap for you, and it's like Bitcoin mining. The first one who fulfills the swap gets the fee. This is the fee. There's no protocol fee. It's just the CCR fee. Whoever is faster to claim the CCR fee gets the fee. It's kept at a reasonable amount. 0.1% for your Igra, Sepolia. 0.1 CAS for TN10. The reason why it's 0.1 CAS is because this protocol was actually designed before Toccata became a thing. This has been in research by me for a long time. And as you may or may not know, division didn't exist on Kaspa until Toccata. So now maybe we should change it, or maybe we shouldn't. So as Pavel mentioned, I'm going to do a demo. I'm going to talk about a bit the demo. What does it do? Because it involves 3 different parts. The first one is Igra Galleon testnet. Risk 0, where I am going to prove locally on my computer right now. And then we have Kaspa L1 TN10, where we execute the opzk precompile. So basically, as I mentioned before, Stromnet uses atomic swaps. It doesn't use ZK. But let's think a bit and say, what if it used ZK? Well, how could we do it? So there's, it's not necessarily that this is going to happen. It's just part of the demo. I want to show you the pipeline end to end, how to interact with ZK covenants. What are we going to prove here? We're going to prove that under Igra state root R, with contract C, that is the HTLC contract, the Strom HTLC v1, with some particular swap ID, has its packed storage word ending 0101. So initialized equals finalized equals true. So I'm going to elaborate a bit more about what this means. The swap ID is the unique swap ID for every swap. Each swap has its own ID. We need to distinguish swaps from each other. A packed storage word is Ethereum lingo for how if Ethereum node stores data. But essentially what is meant here is that we're proving that a swap ID has been finalized, that a swap happened. Right now this is not useful. So I'm showing you this as an example of what you could do to get your creativity going. Perhaps you will do something that is actually useful. So essentially, how are we going to do this? We're going to retrieve a proof, an account proof, and a storage proof from Igra. Igra is an EVM-based system. That means that it has the same principles as Ethereum, which is that items are committed in these so-called Merkle-Patricia trees. And we are able to take specific parts of them and prove that they happened. So let's get started. First off, I want to show you Stromnet because we need to actually do a swap to prove that it's finalized. So we're asked here, I'm sorry if the contrast is not good enough. It's easier to see on the screen. In any case, it asks us from which chain do we want to swap. In this case, we want to swap from Igra. And on which chain do we want to receive? Let's simulate a decentralized exit. We want to receive on Igra, Kaspa. Now we put in how much we want to swap. So I'm just going to check how much we can swap. Okay, we have 69 CAS. Let's try 50. We see that it's $1 here. Let's get a quote, see if anyone responds. Someone responded. So basically what happened here is that this is an LP running. This is my LP. My LP is running on a server. It saw a quote and it said, okay, here is the quote you get. Right now, each LP node can set their own spread. So because obviously swapping is not free, infrastructure is not free, you have to pay for what you use. In this case, it's about 1%. 0.1. Let's continue. Almost there. We need to put in our Kaspa address. I'm going to take my Kaspa wallet here and confirm the swap. Transaction request. So what happens now? In the background, this website is running Rust WASM. It locked your ICAS on Igra. We can check the transaction here. We create a new swap. We can take a look at the details here. So what is inside here? We have an on behalf of, which is our address. This is my address. And we're telling the receiver. The receiver is the LP node that we interacted with before. It's here. There's also a sender destination address, which is my receiver address, but on Kaspa, because I wanted to swap from Igra to Kaspa. It's here. Then there's a secret. We give the secret hash. We inform the LP, you need to lock your funds here. But what if the LP doesn't do that? We have already locked our funds. There's a refund. There's a time lock. This timestamp, when it's reached, your swap can be refunded and you can get your money back. This is why it's atomic. This is why either you swap or you don't. There's no situation where you lose your funds as long as the HTLC contract is secure. The destination here is a protocol-specific destination for which chain we are swapping to. The Stromnet protocol defines the 0 as Kaspa TN10. There's a unique swap ID as well so that we can keep track of transactions. Now, as you saw, it was pretty fast because this LP node was configured to only wait for one block confirmation. However, some LP nodes might have different risk appetite. They might wait for longer or shorter. It's up to them. Let's take a look at the HTLC v1 transaction. So if we go here, you see this is 0xEB. This is 0xEB. There was a claim here right after the initialization. This is the LP node who's claiming their funds because the swap has already completed. The claim here is basically a swap ID and a secret. And that's how the LP node can claim their funds. Now, we went from Igra to Kas. Let's check the Kaspa wallet. Let's go to TN10 Kaspa stream. Shout out to Super Typo for such a great explorer. We swapped 50 Kas. Current time was 1:17. And here's a transaction of 1:15. We received the Kas. The swap is complete. It's atomic. It's done. So this is a decentralized and non-custodial way of exiting Igra. Right now it's on testnet, and it needs to remain on testnet for a long time, for quite a substantial amount of time, in order for it to be tested enough to be going on mainnet. Now back to our actual demo. Because, yeah, we wanted to prove that under Igra state root R, contract C, blah, 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 blah. We basically want to prove that a swap is finalized. Let's go to the demo. So first off, let me go to my demo here. So first off, we need to, let me see if I can increase the code size a bit. Yeah, this is better. Okay. First off, we need to retrieve the account proof and proofs from Igra. We do that by building a witness here. I'm just going to briefly show you the code. We retrieve eth-get proof from the Igra node at a particular slot, which is how Ethereum stores data, and we retrieve the latest one. We basically retrieve an account proof for a particular address, which is the Stromnet HTLC v1 address. Let's do it. It's broken up into 3 steps. The first one is the locking mechanism, because as I mentioned before, we have to lock funds and provide some kind of spending condition. Let's take a look at what spending condition, because this is the fun part. Here is actually this smart contract that we're writing. So we are saying that for some journal digest, which is the output of the ZK program, for some image ID, which is this specific RISC-0 program, for some hash function, these two are RISC-0 specific and don't really give you meaningful value from the perspective of understanding this example. But these 3 are most important. The journal, which is what we want to prove, the output, which we want to prove, the image, which is binding to what program are we saying that it has outputted something. We also have the tag. In this case, it's a succinct RISC-0 program. And then we also add the opcode of opzk precompile. We're going to execute this on TN10, which has already Toccata enabled. So let's execute it. And we need to pass in the swap ID. That's not a swap ID. Yeah. So as I mentioned before, this was claimed by the LP node. So we should enter it, get the swap ID, and lock it. So basically what is happening right now is that it is executing a RISC-0 program in order to compute what will be the output of this program. Because as I mentioned before, there's a journal hash, which is the output of the program. So you need to execute the program before locking it. Because if you don't execute the program, you don't know what comes out of it. So you need to execute it before. But that's flexible. It could be the case that you can just make your script say that it will unlock under any output from your program. In this case, I bind it to a specific journal digest, which is here. This is the hash of something. I will show you what it is. This is my RISC-0 program to the right. To the right is what we're actually executing here and getting a proof for. Essentially, what we're doing is verifying a witness, which is another fancy word for a proof. And then we're building the journal, and we're committing the journal. I will briefly show you the code of the verification. But I plan to release this full code so that you can run it yourself and get familiar with what I have done here. But essentially what we're doing is that we have received the account proof and the storage proof, and we are verifying it inside of ZK that it's valid. And that allows us to say, this data is valid. This data exists on Igra. This swap is finalized. Essentially, this will allow you to prove any kind of state on Igra, or it doesn't have to be Igra. It can be any EVM chain that something happened. It could be the case that other chains allow this flexibility as well, but that depends on their individual implementation. So the locking script, it locked 1.5 cas into the script. And basically we have defined it, as I mentioned before here, that this is the script that we have defined. And we lock 1.5 cas to this script. We can check it. If we copy the transaction ID and go to the Kaspa Stream Explorer, we can see that there's an output here because I spent something here, and then here's the output. As you see, it's a script hash output, which means that it has locked to a specific contract. Now, if we look inside the script, we actually just see that there's only 3 opcodes here. This is the P2SH pattern that I told you about before, because this is the hash of this. So basically, when we want to spend this script, we need to provide the script, and then it will execute accordingly. We have locked the cache. We need to generate the proof now. Let's take a look at the proof generation. Run prover. Let's see what it does. It basically executes this risk zero project. I have basically combined these into nice little scripts that we can just execute. But we can take a look at the proving script. So we're executing this. Let me just minimize a few things because there are different branches. So we parse the witness here with Rust code. It's a bit, there are quite a lot of things going on here. I'm just going to describe a few of them. We pass in the swap ID, as I mentioned before. This is the unique swap ID for each swaps. We have the contract address, which is the HTLC contract. And then we have these Ethereum complex proofs that basically allow us to assert that something happened on Igra. Now, after we have these, we execute it first locally, but then we set up a prover. We set up a prover, a default risk zero prover, generating a succinct receipt. We prove it, and then we verify it. Let's go back and see how it's going. As you know, proving is very expensive. Let's take a look at my CPU really quick. R0 VM is using 7 cores. You don't have to prove locally. There are proving services available that allow you to offload your proof and go into a big prover network which has a lot of GPUs and allows you to basically make it faster, because obviously a production application that requires some things to happen very fast is not possible if you just prove it locally all the time. But for example, rolling up a batch of transactions, or for something that happens not that frequently, it's possible. As we can see now, we have generated a proof for this image ID. So what is this image ID? This is this image ID. It's this verified that I created. If I were to change anything, if I were to change anything inside this code, this image ID would be different. If I were to change the output, this journal digest would be different. Same thing with the control ID. The seal here is the actual proof. This is 222 kilobytes, which is also why in the Kaspa Toccata upgrade, we raise the maximum size of how much data you can push to 1 megabyte. Now, we can unlock the script. That was very fast because the verification of Zinke proofs happens much faster than the proving stage. Verification for Stark proofs is essentially a few rounds of querying something called an IOP oracle. For Groth 16, it's verifying one simple math expression. The proof was valid and the cast was released. Let's take a look at the Explorer. The Explorer is down. That's very unfortunate.
It happens with Kaspa Toccata. Sometimes lagging.
Yeah. Yeah, so it's very unfortunate that the transaction is not found. As you can see, I can no longer reproduce this because the transaction is already spent. Yeah, there's unfortunately not much that we can do here. However, there is technically a way, because the journal, no, there's no way. No, there's no way. Okay, so it's a bit unfortunate. I'm going to continue this presentation. In the background, we will retry this example so that I can show you the final transaction, because that actually contains all the opcodes. Just a briefly reason for why that the Explorer is down right now is, as Pavel mentioned, it lags behind. It doesn't have the necessary hardware at the moment. But this is something that the core team is fixing. So I'm going to go back to the presentation and continue a bit. Then we will go back and see if we can unlock this, because as you saw, I retried locking. Let's see if we can check if this transaction is indexed now. Okay, yeah, this one is indexed. Okay, so maybe if we wait for the proof to complete, we can retry the operation. In any case, we'll continue. So basically, soon, hopefully at least, we will have proven that this is true. But what happened? What happened? We created a swap on Igra with the Stromnetz system. We executed a RISC-0 program that proved that something happened under Igra state. Then we have a Kaspa L1 covenant verified the proof by KIP 16 and released the funds. The issue here is that we were not able to verify it, but hopefully we will be able to. So I want to just briefly state from this example is that you should not take this code that I will release and use it in production before some things need to be done before it is a sound. That's because many times I mentioned R. R is the state root that we verify against, but it could be completely arbitrary, because I could take an Igra clone and basically state that something happened on an Igra, but actually I have a one-to-one clone with Igra. So this is not a sound example. And for it to be sound, the Igra attesters could publish a state root. If Igra attesters publish the state root on the blockchain or on L1, let's say, then anyone with a ZK proof can prove anything on Igra. So it's a matter of just the testers publishing this data. Let's go back to the example. It's still proving. Let's see if there's something I can show you. Oh, that was lucky. Okay, proof is done. Let's unlock it. Now we finally got a spend transaction. Let's hope that it's indexed. It's very unfortunate. One second. Because I couldn't show you the exact example, I'm going to show you something which I did yesterday, where I ran the exact same operation. The interesting parts that I just want to show you is the opcodes that were provided here. So, as you can see, we have a covenant redeem script, and the Explorer has decoded some parts of the script. Now, we can see that it has detected it's a ZK precompile, and we can see the actual input that we provide. For example, the 21 tag, which is the RISC-0 tag. We also see our proof, which is this very large piece of data here. It's 222 bytes. And yeah, that concludes this demo. Thank you for listening to me. Here is a QR code to my X profile. And if you haven't followed me, it would be, I think, if you enjoyed this presentation at least a little bit, even if it was very long and perhaps boring at some parts, I will keep posting about relevant information that is related to Kaspa, to ZK, to perhaps Stromnet as well. I will continue my mission into making Kaspa as developer friendly as possible, because that is my ultimate goal. Thank you for listening.